Today's videos are about a machine vision topic called features. In machine vision parlance, a feature is any property of an object that can be determined from an image of that object. Features include such things as color, size, dimensions such as height and width, and even the shape of the profile of the object. Basically, features of objects can be used to help us do three different important functions. Features can be used to help us ignore objects that are not of interest. For example, in the lab that we did last time, we processed an image with our image segmentation algorithm, and then we looked at how many different objects were identified by the algorithm. Even though there were only maybe a few dozen objects in the image, the algorithm came out with something like 3,000 individual objects. The reason is because the image has some noise, that is, black pixels in locations where we don't intend there to be black pixels, or white pixels where we don't intend there to be white pixels, and each of those little bits of noise is picked up as its own individual object. One way to get rid of all of these little objects that are due to noise and not due to the actual presence of objects is to use the concept of features. So we can use features to ignore objects that are not of interest. The second use of features is to allow us to focus on objects that are of interest. For example, we might be especially interested in objects that are of a particular height and width, or a particular color, or of a particular size range. The third use of features is to find the identity of objects. For example, the use of features can allow us to distinguish between an object that is a house, or a car, or a person. Let's take a look now at how we can use features to accomplish these three operations. The process of getting features from objects is called feature extraction. The process of feature extraction will be different depending upon what features you're trying to extract from objects. However, the input and the output of a feature extraction operation is always the same. The input in a feature extraction process is the object matrix. Remember that the object matrix was the output of our object labeling algorithm. Here, the object matrix is the input. After applying the feature extraction process, the output is something known as a feature plot. Let's take a look at what a feature plot is. A feature plot is a plot in a space that we call feature space. Feature space is a space in which each axis represents one feature that we have extracted from the objects. For example, let's suppose that we've decided to extract the features height, width, and total size. In this case, we need to have a three-dimensional feature space with one axis representing the height of objects, one axis representing the width, and one axis representing the total size. In feature space, we will plot one dot for each object that has been extracted with our image segmentation algorithm. For example, let's imagine that we have applied the image segmentation algorithm to an image, and the algorithm has found 1,000 different objects. We can know how many objects were found by the image segmentation algorithm by looking at the largest label number that was applied to any objects in our object matrix. Next, we will create a loop. This loop will iterate from 1 to the number of objects found, in this example 1000. Within the loop, we will calculate the size of object I. The size of object I will be equal to the sum of all of the pixels where the object matrix is equal to I. This will tell us the total number of pixels that have been assigned the object label I, and that will tell us the size of object I. Next, we can calculate the height of object I. The height of object I will be equal to the difference between the maximum non-zero row and the minimum non-zero row. Note that we're doing this for every single object that was found by the image segmentation algorithm. That means that we're finding the values of size and height and width, not only for the objects that we want to pay attention to, but also to the objects we'd rather ignore. We can also calculate the width of object I in the same way. The width of object I will be equal to the maximum non-zero column of the object matrix I minus the minimum non-zero column. In other words, if the first non-zero column of the object matrix is column 3, and the last non-zero column of the object matrix equal to object I is 10, then we would say that the width of I is the difference between those two, 7. And this is the end of our for loop. Once we've gone through this entire for loop, we will have calculated the size, height, and width of all of the objects found by image segmentation. We will then take the size, height, and width for all of the objects and plot them as vectors, where each vector consists of 3 elements: the size of object I, the height of object I, and the width of object I. We'll take these vectors, a total of I vectors, and we plot them into our feature space. What we'll find is that some of these objects will be grouped near 0. Some of the objects will have unusually large numbers in some of the features. For example, some of the features will have unusually large or small sizes. Unusually large sizes often indicate an object that was identified from the background of the image, and unusually small sizes often indicate that these are objects that are image noise. Some of the objects in our feature space will be grouped around an area that is particularly of interest to us. For example, let's suppose that we are trying to use image segmentation and feature extraction to focus only on the images of people in the camera scene. We can eliminate objects that are not of interest to us by knowing approximately what is the size, height, and width of the image of a person. We can ignore all of the features in our plot that fall around the very small or the very large range, because we know that no image of a person would fall in these ranges. This can allow us to ignore objects that are either due to image noise, the background, or even legitimate objects that are not the people that we're looking for. One way to use the features in feature space to allow us to ignore objects that are not of interest is to use an if statement. For example, we can have an if statement that says if the size of object I is greater than some value, then we can remove the object from the object list. Or if the size of the object is too small, if it's less than some number, then remove the object from the list again. We can use if statements like these to pare down the list of objects, to ignore those objects that are not of interest to us, either because they represent things that are not really objects, like noise or the background, or because they represent legitimate objects that are not the objects that we're looking for. Besides if statements, there's another way that we can use feature space to find objects that are of particular interest to us. In feature space, if we know the approximate size, height, and width, or whatever features we've chosen to extract, we can define a point that represents the ideal object. For example, let's suppose that we know that the ideal height, width, and size of a person in our image falls right here. This one point that I've just drawn represents a specific size, height, and width. Now, objects that we pick up from the camera are unlikely to match specifically exactly the size, height, and width of our ideal object. So what we do is we define a radius that is a distance away from the ideal point. This is a radius. Any objects that fall within a sphere or a circle, depending upon how many features we are using in our feature space, will be identified as an object that we are interested in. And any objects that fall outside of this sphere or circle will be identified as an object that we are not interested in. And here's how we do that. First, we would identify the ideal feature vector. And we would define the distance away from that ideal vector that is allowable for us to recognize the object as being an object of interest. Next, we would go into a loop that, like our last loop, cycles through all of the identified objects. Inside of this loop, we would calculate the distance between each feature vector and the ideal vector. Here I've shown single vertical lines to represent the absolute value of the difference between the ideal vector and feature vector I. Next, we'll check to see if the distance for object I is less than or equal to r. If the distance is less than or equal to r, then we keep the object in our object list. Otherwise, we do not keep the object in the list. I'm going to show you briefly graphically what this approach looks like. Back in our feature space, we have shown in orange the ideal vector, and I'm going to draw an arrow from 0 to the ideal vector to represent that this point is a vector. Now, if we find an object located somewhere else in feature space, I'll draw a point here somewhere else in feature space. This point is a vector. By subtracting these two vectors, we find the distance between the ideal vector and the vector of the object in question. We then check to see if that vector is less than or equal to r. If that vector is less than or equal to r, then we know that the point in question, shown here in purple, falls within the sphere of allowable feature vectors. That means that we're interested in that object. Feature vectors that fall outside of the sphere are deemed uninteresting, and we can ignore them. This approach is also the kind of approach that we use for object identification. And now I'm going to show you a little bit about how object identification works. To give you an example of how object identification works, I want you to imagine that we're trying to use our image processing to detect the difference between three animals: horses, rabbits, and dogs. If we want to use machine vision to determine the difference between horses, rabbits, and dogs, we have to start out by deciding which features of the image would be useful for us to capture. In general, we want to use as few features as we can, but we need to include enough features to allow us to tell the difference between the different objects we're trying to identify. Figuring out which features are important to capture from your image in order to identify the objects in question is a process known as feature selection. For the example of trying to detect the difference between horses, rabbits, and dogs, we might decide that the features that we need are size, color, and speed that the object is moving. I don't know if these really would tell us the difference between horses, rabbits, and dogs. We'd have to try this and see whether or not it works. In fact, much of the process of feature selection involves taking a lot of images, trying out which features are relevant and which features are not relevant, and seeing whether the object identification is successful or not. It takes a little bit of trial and error. But for this example, I'm going to suppose that we're using size, color, and speed. The next thing that we're going to do is draw our feature space. Since we're using three features, we need to have a feature space that is three-dimensional. One dimension will represent the object size. One dimension will represent the object color, and the last dimension will represent the object speed. Next, we need to identify the ideal size, color, and speed for each of the objects that we want to be able to identify. For example, we might decide that the ideal size, color, and speed for a rabbit is a small size, a slow speed, and a color that's in the range of, say, white to brown. So I'll place a point in my feature space representing my ideal rabbit point. Next, I'll place a point representing the ideal dog, which might be a larger size and a faster speed, and perhaps even the same color. There's the ideal dog point. And the horses will be the largest size and the fastest speed. Now, for each of the objects identified by the image segmentation algorithm, we will do a feature extraction process to determine the size, speed, and color of each object identified. We'll then place the object on the plot in whatever point represents the size, color, and speed for that object. If we assume that all objects are either rabbits, dogs, or horses, for example, supposing that we've already put the objects through the process of eliminating all objects that are not important to us, then we'll take each unknown object and calculate its distance, that is, the Euclidean distance between the two vectors. We subtract the two vectors and take the absolute value to determine the distance of the unknown dot between the ideal rabbit, between the ideal dog and the unknown point, and between the ideal horse and the unknown point. Whichever of these distances is shortest, we can classify the unknown point as that object. This approach tends to work well if your environment is very controlled. For example, if you know or can assume that all objects in view are either rabbits, dogs, or horses. And it tends to work well if you've done a good job of choosing your features. If you don't choose the right features, this object identification process can fail. For example, suppose that we had chosen to not include size and speed in this feature space. It may be that rabbits, dogs, and horses all have approximately the same available possible color range. In that case, trying to tell the difference between rabbits, dogs, and horses based solely on color may not be successful. We can also improve the results of our object identification scheme by using some artificial intelligence approaches like machine learning that we'll be learning later on in class. In fact, once you've been able to convert images to an object matrix and then convert the objects in the matrix to feature space, there's a large number of more advanced and more complex methods that can be used to have better results with your object identification algorithm.